Hi everyone, my name is Rajesh. In today's video, we are going to build a linear regression model completely from scratch. No libraries, no shortcuts. We will walk through the math step by step and then turning that math into an working model written in pure C. Once our model is built, we are going to compare it directly with sklearn's linear regression to see how our model close to the result and also using the same dataset. So why do this? Why to go and create a separate video for this? So if you're learning a data science or machine learning or AI or any such platform, you probably already know the linear regression on the higher level, how the things works, how the weight, bias, predictions are sets. That's all. But what I noticed while learning this, like most of the tutorial are stayed in very high level, and when they use library, everything feels like a black box where we just call dot fit or dot predict, and everything just seem to works. But we don't really understand what is happening underneath. So today we will break down the black box open, we are going to understand exactly how the linear regression works, the mathematically and programmatically. In this video, I have divided it into three parts. First, the math, what is behind the linear regression, how we do it. We will start by manually computing everything into a small data set. Then we will understand the hypothesis, calculate the prediction manually, compute our cost, drive the gradient and perform one full updates. Then we will be building the linear regression in C, implementing the prediction, then implementing the cost gradient, whatever we saw in math, we will implement it exactly and then test our prediction with a small data sets. And finally, in the third part, we will compare it with the sklearns. We will train a sklearn's linear regression model on the same dataset and compare the weight, prediction, and accuracy to see how close our implementation is to the industry standard ML libraries. Alright, so with this plan, let's jump right into the math behind the linear regression. So linear regression is the general idea is to fit a line which best represent the relation between the input and output parameters. If these dots represent our uh, prediction related to the x coordinate and y coordinate, and we try to fit a line through that to make our prediction. The general formula of line is given as y equal to b plus mx, where y is the result, x is the input, and b is bias, and m stand for the feature width or slope in math. We represent the same in program as hypothesis of 0 with theta 0 plus theta 1 x1. This is as we have only one input, this is known as simple linear regression with one input parameters or features. When we have multiple input features, we call this as multiple linear regression. That what we will be doing today. And this is the formula for for the hypothesis of multilinear regression. I stands for the number of row or the no row of the operation. Theta 0 as bias, theta I and theta 2 are the feature weights. Our goal is to find the value of theta which will best represent our line. And how do we find that value of theta? We do that with something called gradient descent. And uh, and there are some popular choice of gradient descent. Those are batch gradient descent, stochastic gradient descent, mini batch gradient descent, which is most commonly used along with the stochastic gradient descent. But in today's example, we will see how batch gradient descent works to calculate the value of theta or the slope. So the formula to update theta is equal to theta minus alpha learning rate with our derivative of our cost function. In this example, we will be using half MSE cost function or mean squared error. The formula of uh, cost function goes something less 1 by 2m summation of hypothesis of x of I minus y of I, where the total h of 0 of x of I we represent it as h, and the total value hypothesis of x of I minus y of I is known as the error. Deriving this formula, we come to this formula where h minus y is error, which we'll see going forward. Then, so our formula, final formula to update the theta value comes to theta k equal to theta k minus alpha of 1 by m summation of h minus 1 of x of k. So, for example, let's take a uh, input of x which is having two features x1 and x2, and the resulting is y, and the number of samples is 4, which m equal to 4. Before we start, we will add interceptor into our input vector, where we will take x0 as all 1. This is known as the interceptor, and the initial theta is all 0 for the three features, and alpha will be our learning rate starting. So iteration 1, our first step is to calculate the hypothesis, where h is theta 0 into x of 0 plus theta 1 x of 1 plus theta 2 x of t, where the first for the first sample, after the calculation we get 0 naturally, as we have all our theta set to 0 for first iteration. So for all the samples we will be getting 0. Next step is to calculate our error. So our hypothesis, we will put this value over here and subtract it with the predicted value, that is our results, actual result. We'll subtract it with that, and we will get minus 6, minus 8, minus 12, and minus 8. After that, we will be calculating the gradient g, whose value is 1 by m summation of e of k transpose, where x of k, uh, as shown here. We can take a matrix dot product, but here we will be going with simple math algebra. So solving the dot product, we'll have minus 6 into 1 plus minus 8 into 1 plus minus 12 into 1 plus minus 12 into 2 whole divided by 4. So we'll get something as 8.1 for the first theta value, minus 6.5 for second theta, and 17.0 for the third. The last step is to update our theta values, where we will do with this formula as we have seen before here. So we'll now multiply with the theta value and our loss function. Yeah, so updating it, with our learning function and subtracting, we'll get 0.85, 1.65, 1.7. And finally, as a summary, we will calculate our loss function, half square loss function, which we have seen before, 1 by 2m summation of h0 x of I minus y of y whole square. Computing it, we will be getting 338.5 finally. So at the end of the first iteration, we have our theta value of this and our loss function of this, where we had calculated the gradient of this. Going forward, we will be putting this theta value to our second iteration. At the first iteration, as you remember, we have to call this value as 0. So step 1 again, to calculate the hypothesis, putting this theta value with respect to each input variables, we will be getting this results. Then we'll move forward to calculate the errors, and after calculating the errors, we will similarly calculate the gradient descent with the same formula, and finally updating our steps where the theta values, and then we will calculate before updating our theta value, we must calculate our loss function, and this we will continue throughout the equation. So now let's move on to the coding part, and we'll see how exactly we will code. We will having this folder structure where in the data we will be having our CSV file. This is the same that we have seen in our math calculation. Then in shared C, where we will be having our common C module, we uh, have our linear regression model we will be doing up here. Then we will be using PyBind to import our C programs to the Python. Here is the source C where we have the main file, and the Python and IP file where we will be doing it after we create our model. So this would be our folder structure. So let's go ahead and start with the main C. Let's import our files. These are few imports. As you can see, I will import others. We will be creating a custom data structure to define our uh, input, data set, of double, which will be our x, and then vector double, which will be representing our y. Let's have a function to import our CSV dataset into our C programming, which will return our dataset. String in CSV. Define our dataset as string line. Let's keep the header line. string stream ss line string cell vector double row. Single quote here. Row runtime error. Okay, so now we have completed the function. Let's use this function and import our CSV file in the main function and let's print a few lines. Using now let's move to the linear regression where we will be building our model. We will be importing our linear regression here. Code. This is a simple class where we will be writing our code. Algorithms image if iOS team expects string vector limit, and we also need using namespace string. We will simply create a constructor public explicit linear regression, which we will be taking the double rate, learning rate, double learning rate will keep at default 0.0001. Learning rate equal to learning rate, comma, theta. We'll have a function called void fit to train our model. We will set the learning rate and theta as private double rate vector double theta. Then we should have an then we will be having a predict function void predict predict. Then we will also pass down the theta if needed. So for that we need a function vector double coefficient will just return theta. Okay. So in the fit function we will be having the input vector 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 of double of x. We should also take the vector, sorry, we will be taking the uh, prediction, which we called as, so linear regression will have one constructor. This will be our default constructor, and we will have a fit function and a predict function with a coefficient function returning the theta. uh, X is our input, y is our actual prediction or the actual value. Int, we will be taking number of iteration we need to perform. Epoch will set as default as 1000. It's just a small one. Then we will first we will check if our datasets and labels are not empty. So if x dot size equal to 0, or y dot size equal to 0, so invalid argument, empty training data or label. Stm equal to x dot size, then number of features, size for number of features, FEFGRA features equal to x of 0 dot size. Then we will check if we have uh, number of samples is equal to number of label. If y dot size is not equal to m, throw invalid argument, mismatch number of sample and labels. See, here we will be initializing our first data, theta value as 0, theta dot resize number of features plus 1. and we will set default as 0.0. Why features? If you recall, we have taken the total number of features plus the interceptor as number of theta. So next we need to add interceptor. Vector, vector, double, x intercept equal to x or size t I equal to 0, I is less than m plus I will be adding interceptor, that x intercept of I dot insert x intercept of I dot begin will with 1.0. Now we will set some values which we will be using going forward. For example, we will be setting a vector for error, for gradient, and for our hypothesis. Vector, double, error. The size of error will be the size of our samples, and we will initialize all with 0. Vector, gradient, double, gradient, whose size will be as much as our features plus 1, we will initialize it 0.0 as we will be calculating it later. Then for our prediction or hypothesis, double, which will initialize as m number of samples at 0, initialize as 0. Now for each epoch, int epoch equal to 0, first epoch, where epoch is let the epochs plus epoch, size t int equal to 0, I less than m. We will be doing it for all the samples plus I. We need a value double hypo to 0.0. So if you remember the formula, we will multiply with the features with the x value along with the interceptor for the first one. So we will do exactly that. For size t, j equal to 0, j less than features plus 1 plus j plus j hypo plus equal to x intercept of I j to theta of j. And we will add this to I of psi. So this is how we calculate the hypothesis. Next, we will be calculating the error. Step 2, calculate the error. For size t I less than m, error of I equal to h of I minus y of I. Simple, pretty straightforward. For third step, we need to calculate the gradient. Calculate the gradient. To calculate the gradient, we will do it by multiplying the error with the x value and doing the sum of all the features value. So to do that, we will do it like size I equal to 0, feature where I is less than feature plus 1 and I plus plus. Then we will take a value as a double, grad equal to 0.0 initially. For size j equal to 0, j is less than m, we will run it for each number of each number of sample 1, 2, 3, 4, and we'll go that. So our grad will be grad equal to plus equal to error of j, error of j multiplied by x intercept j of I. And finally we will insert this into our gradient vector. Gradient vector I equal to, as you remember, after adding all this we will be dividing by the number of samples. So we will be doing like 1.0 by m into grad. Our fourth step, as we have completed this one, the fourth step is to update the value with the formula theta j equal to theta j minus alpha of gi. That is our gradient. Step 4, update the theta of double, vector of double, new theta equal to theta for ti, where I will be less than feature feature plus 1, features plus 1, double update equal to theta of I minus the learning rate into gradient of I. New theta of I equal to update. And then after the value, we will move that, update the theta value, theta equal to move new theta. This marks the completion of our linear regression model. After that, we have a summary to implement the cost function to see how well our uh, model is working. So let's just quickly do that. Semi double MSE for each epoch 0.0 for double E in errors MSE equal to epoch plus equal to E into E. We did the square. Now we have to divide it by 2. 2.0 into m. This follows the formula of 1 by 2m summation of hypothesis minus the actual prediction whole square. At the end, we will be printing uh, a summary for our updates. Let me just quickly copy paste that. Now let's try to call this into our main function. See if we can like call the fit function or not. Main.cpp. First and foremost, let's import that. Include shared C model supervised linear regression. Just copy paste it, not to make any mistake. Dot cpp. Okay. Then let's just call that linear regression model equal to linear regression, and here we have to pass our learning rate. We are keeping it small because we have really small data set. We have data set of 4. So let's try to fit model dot fit ds dot x comma ds dot y. Right. And let's run it for 100,000 inputs. Let's try to get the coefficient. Model dot coefficient. Save it. Auto cos equal to. We need another function to fit our fit. Sorry, we need another function to predict any of this. So let's go ahead and write those fit predict function. So our predict will return the prediction, which will be of type vector. It will be of type double. sorry, double const vector double x const. If theta dot is empty, throw time error, model is not trained yet. Then take vector double features equal to x, we will add some checks. If features dot size plus 1 equal to theta dot size, will insert features dot insert features dot begin plus 1.0. Adding interceptor here, else if feature dot size is not equal to theta dot size, throw invalid argument, input feature size mismatch. Then we will calculate the result double and result equal to 0.0 for size of t, feature dot size, feature dot size result plus equal to feature of I to theta of I, then return result. Okay, so this is our predict function. Okay, let's go ahead and run this to see if we have any error or not. Auto predict equal to model dot predict. What should we predict? Let's get a new sample. Vector vect vector double new sample equal to 879 auto predict pred equal to model dot predict new sample cout expected expected 8 8 from 1 comma 3 pred okay, let's now try running this. First we need to build, then run this. We're expecting 8 from 1 and 3. Oops, we are getting 0.27, where we have run for 1000 epochs. 3.7 to 3.59, where from each epoch we are gradually able to reduce the our cost function from 3.5 to 3. Uh, let's try to import a larger uh, dataset and see how well our model perform. Let's import this student performance for EDA and ML. Okay. And let's delete this, and we need to change here student student performance performance.csv. Let copy one of this, and now let's try to run this one. Okay, theta value MSME value is 3.4. Let's try to reduce the cost function. Let's tweak this a little. Okay, so now we are able to get pretty much near value. So if we tweak with the number of epochs and our rate of learning, we may get a more accurate value. But let's let ahead and let's move with importing it and comparing it side by side with the C program. So let's move ahead and write our pbind code 11 module shard c ext. This will be our name. Use name space py class linear regression linear regression dot diff. We need to define our input fields for init. Okay. C++ sklearn. let's go for code and let me just add this. So in this, we're trying to import the student performance dataset from the data folder, then getting the shared C that we will be building for that, and after that, importing two times. Okay, then we will get the dataset. We will use the PD uh, pandas library to get that features along with the target X and Y, which we will be then splitting the dataset for prediction, and we will have a same epoch and learning rate for both our C plus model as well as sklearn. So this where we import our model and also calculate the mean square root by the help of uh, this Python function. So we will have the similar score along both of the model. After that, here in the summary, we will see how well our what is the result of I mean MSME result is given, and then we'll show the prediction of few side by side what the C predicts and what the sklearns predict. Then we will also visualize it. This where we calculate the R2 scores for both of the for sklearn's linear regression and as well as our linear model, and we'll show it in a graph. Let me just quickly build the CX run from PyBind. Let me rebuild this. Scene data run. Okay, now our PyBind has been successfully completed. Let's try and running this. Okay, it seemed to have run successfully. In the side-by-side comparison, as you can see, the half MSM is square and the prediction of our prediction side by side with the sklearns. Let's see the accuracy. So the accuracy is nearly or same to us. So following this, like you can tweak and see how we build. I will be attaching this commands in the file and I will be uploading it. You can find the GitHub link in the description. So let's quickly have a overview of what we did. We implemented a linear regression model with a fit function following all our steps. First we added the initialize the theta value, then added the interceptors along. Then for each epoch, first we calculate the hypothesis, then calculated the error along with the gradient descent. Then we went ahead and updated the theta value, but before updating we updated the MSME or our cost function. and then we have uh, we have printed our epochs result. Then we had a predict function where we take the input vector, add the interceptor at the beginning, then with the features and with this theta value we try to calculate the result. Then we went ahead for uh, predicting the dataset into the Python notebook. Then we train with learning rate of 0.05 and 1000 epochs into our model. This is our C++ model, and this is the function we create. Then following that, we use sklearn's HD regression with matching hyperparameters. We'll use the same learning rate over it and epochs, and these are some hyperparameters you can tweak and see. And then we went ahead and displayed the accuracy or half MSME square what result each models gives. After that we went ahead and tried to visualize with the numpy and plot bar. We used a bar graph and show it where we got the accuracy and in percentage over here for both the sklearns and the test. So this marks the ending of our video. Thank you.